presentar delante de tanta gente joven. I will be giving my talk in English, actually, because it's easier, and also maybe there are some people in the audience that don't speak English. And I will tell you about experiments that we do in my group at ICFO. So ICFO is located in the outskirts of Barcelona. It's like the Leioa of Barcelona, 20-minute drive from the city center, and very, very close to the sea, as you can see here. And then what we study in my group are Bose-Einstein condensates. So states of matter made of many quantum particles, all in the quantum, in the same quantum state. And because ICFO stands actually for Institute of Photonic Sciences, so it's an optics institute, we decided that we had to take our Bose-Einstein condensates and dress them with light to see what comes new. And that's what you can see in the title of my talk. So we use optically dressed Bose-Einstein condensates, and we use that for simulating some new exotic superfluid phases. So more generally, let me tell you a bit more about my research field. So what we are interested in my group is really the physics of quantum many-body systems, to have systems of many quantum particles that are interacting with each other. And because you have many and because of their interactions, then you get new physics that emerges. So collective phenomena that can be like superfluidity, the fact that you have flow without any friction. So you can have superfluidity, flow without friction. You can have superconductivity, and here you see a high TC superconductor levitating in a magnetic field. Or you can have some macroscopic quantum coherence, as we see in Bose-Einstein condensates. And all this comes, really, these are effects that come beyond the physics of a single particle. So really, as Phil Anderson put it, more is different. Now, if you want to study quantum many-body systems, actually, the first thing that you need to do, for example, theoretically, is just to write a model that describes in the simplest possible way the essential physics that is at play here. And for example, for a high TC superconductor, the model that you write is very, very simple. It's the so-called Fermi-Hubbard model. So you have electrons in this solid that can pass from one side to the other one of the crystal by hopping with a matrix element T. And when they are sitting in the same site, if they have opposite spins, then they are interacting with interaction energy U. So this looks like a very, very simple model, and if you want to solve it, okay, if you're a theorist, you say, well, I can do analytic treatments, try to really compute things analytically, and this turns out to be a too hard problem to solve analytically, so we really don't know how to address it. And you can also say, well, I will put the problem in a supercomputer and have the supercomputer give me the answer, but this problem is also too hard for the biggest supercomputers in the world. And then what we want to do is to address this in a different way. And the inspiration comes actually from what was done really many centuries ago, for example, for hard problems in those times. So these are hard classical problems, like the motion of the planets around the sun, and also the motion of the stars in the sky. And then what people did was to build some armilar sphere where they could actually have some artifact, some instrument where they could move actually the planets and then get the predictions without having to do all the calculations. But we want to do that for quantum problems, so we want to be able to address this type of quantum many-body systems, and what we want to develop is something equivalent to this for these systems, which is some kind of quantum Lego, I like to call it. Yeah? So some building blocks that we can build these models and then let the system just find the answer. So what are the bricks of our quantum Lego? Actually, what we do in my group are quantum gases. So we take vapors that are very dilute, so much more dilute than the air in this room. And actually, if you take a gas at room temperature, the atoms are moving very, very fast. So actually, these atoms, these molecules, they are behaving really classically. Why is that? Because you can think that to each atom or molecule, you associate a wave packet, which has an extent that is given by the de Broglie wavelength. And if you're at room temperature, the velocities are high, and this wavelength is really very small, and the parameter to compare to is actually the distance between particles. So if the de Broglie wavelength is much smaller than the typical distance between particles, then the wave nature of these particles does not appear at all, and that means that the quantum effects are not coming into play. But what we can do is actually to reduce this velocity that we do by cooling the atoms, and we cool them with lasers. That's another reason why we are in a photonics institute. And when we do that, if we do that such that the wavelength becomes larger than the distance between the particles, then we enter the so-called quantum degenerate regime. And then the type of atoms that you have really matter a lot, because if you have bosonic atoms that have an integer spin, they will all occupy the same state, the ground state of the system, and then you will have a Bose-Einstein condensate that forms. And if you have fermionic atoms, you have Pauli exclusion principles, so they will sequentially occupy the different energy levels of your trap or box or whatever you put the atoms, and that's what happens. Yeah? So this, what you can see here, is actually an image that is very dear to me, because this is the first time that we observe a BEC, a Bose-Einstein condensate, in our labs in Barcelona. So you have a thermal gas, and as you cool, then suddenly you see this peak that appears here. This is in the momentum distribution of the atoms, because all atoms go into the same quantum state. And this is really, by now, really the brick that we use for doing our experiments. Is the building stone for everything that we do. Now, how would you solve hard quantum problems with that? So the idea is that you have your Bose-Einstein condensate, and you want to emulate, for example, the physics of a complicated material. So what you actually do is that you engineer the model of this material. Yeah? So you just look in the condensed matter textbooks, so what is the good model for this phenomenon or this other one, and you figure out how can you engineer that with your atoms. And the idea is that some of these materials might have a very complicated behavior that we don't know how to understand well. So for example, if you look, this is one of the proposed phase diagrams for the cuprates, for the high TC superconductors, and you see that, okay, we don't really know how to compute these phase boundaries, or even if some of these phases are here and exist within this model, but we also have many phases also at higher temperatures that we don't understand much, because when you call something strange metal, it might be that you don't really know exactly what is going on in there. And the idea is that if you can engineer that with atoms, well, you can measure on the atoms and also figure out what is there. Just within the model and not within a more complicated material that will also have other impurities and other things. So this approach is actually something that was proposed many years ago by Richard Feynman. The idea of Feynman in this seminal paper, where he also discussed in detail for one of the very first times this idea of quantum computing, is that you can just have a quantum machine that you can use to imitate any quantum system. So you can really use these systems, for example, as armilar spheres for many body problems. And the term that we use for that is quantum simulation, because this is a term that Feynman coined in this paper, which is really something that you can see as some kind of special purpose, some analog quantum computer that is really designed for solving a specific problem, because different complicated quantum many body systems will be described by different models, and for each of these problems you need to engineer a different model. So, I mean, I started telling you that we take our atoms and we cool them down, and then they get into the quantum degenerate regime, because we really have the quantum effects that come into play, because the de Broglie wavelength is larger than the distance between particles. But okay, if you think of a solid, it looks more like something like that. And this is because there is a crystal in the solid, and that's making that the electrons can only occupy certain positions in space. So how do we do that in our experiment? Actually, we start with our ultracold quantum gas, and then we create a crystal with lasers. A third reason why we are in a photonics institute, because we use lasers to create artificial crystals for the atoms. And then with these, basically what we do is that we just create all the ingredients that we need to simulate a solid, because at the end, for the transport properties, a solid is nothing else than the electrons and the crystalline structure. This is really the essence of the solid. And you see it looks very much like an egg carton for our atoms. And if you look at solids, of course, electrons have spin, but we can take atoms in different internal states, and we can have, for example, blue atoms and red atoms, and that would play the role of a spin 1/2. Yeah? Now, one advantage of doing this with cold atoms is that these crystals that we create artificially, we make them by actually interfering laser beams. So that tells you that the spacing between the sides here in this crystal is given essentially by the laser wavelength. So typical spacings in our lattices are 0.5 micron between one well and the other well. And that means that it is possible to directly image them using microscopes. So basically you can take an image and see where every single atom is in the crystal. And this looks like a hand-wavy explanation, but actually this is how our lab looks like in Barcelona. Here Here it's a laser-cooled trap of atoms. Here atoms are about a millikelvin. We can cool them more to reach Bose-Einstein condensation. Now if we zoom in here, you can see that below there is this silverish tube. This is because there is a microscope objective that is very, very close to the atoms, just a bit more than a centimeter. And then with this, basically, we create the artificial crystal here. We shine light into the atoms that is resonant with an atomic transition. The atoms will just scatter photons. These fluorescence photons can be emitted in every direction. And then we can collect a big fraction of them with our microscope objective. And this is what you see. So this is really an image that we took in one of my labs. This is a really very recent image, so we are very happy about that because it's one of the very first where you can see these bright spots, and each of these bright spots is a single atom that is trapped in one of these lattice sites. And you see, I mean, the spacing between two of these dots is this 575 nanometers, is the spacing in our setup. So this is actually something that we can resolve optically. So you can take a region, for example, of this cloud, you see here, and then you can run some reconstruction algorithm that automatically tells you if there is an atom or not. And you can try to see, for example, this L here. Well, you see, I mean, our algorithm really tells us how many atoms are there and what happens with them. So this is actually something that I found very cool because you know these atoms are in this lattice. Actually, when I was postdoc, I worked on these things for many years, but I had never seen the single atoms. It was like, I believe they're like that because everything is behaving like that, but actually we see them there. And this is not something that we invented. This was first demonstrated more than 10 years ago by the groups in Harvard and in MPQ in Munich. But what is new now in our setup, that's what we are excited about this, is that we use a different atomic species, strontium. This is the first time that we can actually make these lattice systems image atom by atom in quantum gases using this atomic element. And this is a very interesting atomic element because it's also the element that is used in the best atomic clocks. So you can actually use all the tools of quantum metrology, very precise measurements of frequency and so on, now to address these quantum many-body systems. Another thing that is very interesting with strontium is that if you see before, I was talking about simulating models of solids, and solids I was saying, well, you have spin 1/2, so we take two internal states of the atom to do like the spin up and the spin down. But actually with strontium, we have a fermionic isotope that has 10 internal states. So we can make Hubbard models, so models for solids that have much larger spin, and there are actually many open questions on the physics, the many-body physics that can appear here, and exotic states of matter that have been predicted, and now we think, well, we can start to see them atom by atom. Yeah? So this is what you can do, for example, if you take these ultra-cold quantum gases and you use them to solve problems that people already told you they are interesting, they are hard, they are there. So it's basically as if you play your quantum Lego game and you just do the model that comes in the instructions. But I always thought when I was a kid, it's much more interesting when you just don't do the model that they tell you to do, but you actually just invent your own models and your own things. And this is also something that we can do, and I would say that this goes in the spirit of what people like Grigory Volovic already mentioned that you could do with other quantum systems like superfluid helium, where he has this book, which actually is full of interesting ideas, that is provocatively named The Universe in a Helium Droplet. So if you have a quantum system, you can actually use it to address many other physics problems and maybe also to invent some new ones. And what I will be talking about in the rest of my talk is what we do in another laboratory, not the strontium laboratory where we do these artificial solids, but one where we study Bose-Einstein condensates of potassium atoms. And with potassium atoms, we can make atoms interact in different ways. We can make them attract, repel each other, interact strongly, weakly. We have this additional tool. And then we will try to see a bit the universe in a potassium Bose-Einstein condensate. And actually, the universe is too ambitious, of course. I did not coin this thing, Volovic did. But we actually can use this system very flexibly to study many different topics in physics. So we used it a few years ago to study quantum liquids, to make liquids that are super, super, super dilute. So the most dilute liquids that exist in nature, but that exist precisely because of quantum effects. They are stabilized by quantum effects, and we could even see some drops of quantum liquids that look very much like these water drops, but quantum. But I will not be talking today about that, because actually last time I came to Bilbao, I remembered I gave a talk in a conference. It was precisely on this. It was back in 2018. So I thought I should talk of what has happened since then. And actually, what we have been studying recently is how we can use these potassium Bose-Einstein condensates, now adding this ingredient of dressing them with light, to investigate another very exotic phase, super solid, and also to simulate gauge theories. And I also chose these topics because I think they nicely overlap with research that is going on here in Bilbao. Supersolids have been studied very much by a group of Michele Modugno, and gauge theories, Enrico has been doing also many work on these for many, many years. So let's start first with supersolidity. So you might have already heard about supersolidity, but let me remind you what this is. So this is a very, very strange state of matter, because it combines the properties of a superfluid, which is a system that flows without any friction, so where all the particles share a common wave function and they have a common phase. So you can say that this system spontaneously breaks a U1 symmetry because there is one phase that is picked up. And the physics of a solid, and in a solid, actually you have atoms that get organized in a crystal, as we saw before. So it's a system that explicitly breaks translational symmetry. But what is interesting in this supersolid is that actually it's a system that spontaneously breaks both symmetries. So you have both things, crystalline behavior and flow without any friction, that appear at the same time. And this is an idea that is very counterintuitive and was proposed many years ago at the beginning of the 70s by people like Andrei F. Lifshitz, Chester, and Tony Leggett. Also has very important papers, very clear papers on this topic. And the idea on those times was to take the most quantum solid that we have, so that's solid helium, and try to turn it into a superfluid. The idea was very cool, and there were many, many experiments that have been tried over really decades. And there have been many false alerts of people believing they see the supersolid, but there was always not an ambiguous proof of that, because there was always some other explanation that could come in place that was not supersolidity to explain the behavior that they were seeing. So actually, because it was such a cool idea, then people thought that maybe one could get this supersolid coming from the other direction. So let's not take a solid and make it superfluid, but let's make it start from a superfluid and try to make it crystallize, but crystallize spontaneously, not because I put an external crystal like this optical lattice, but that the crystal develops by itself. Yeah? And then why did people have this idea? It's because if you look at liquid helium and you look at the excitation spectrum of the system, you have here this linear part. These are phonons, sound waves in the crystal, but then there is a structure here at some finite momentum, yeah, which is called a roton, and that's telling you, like the inverse of this momentum scale is giving you a characteristic length scale, and you can imagine that actually if the energy of this minimum goes smaller and smaller and smaller until it touches zero, then the system will spontaneously crystallize, yeah, at this wavelength that is given by the inverse of this momentum. And this is an idea that was proposed only a decade after the first ideas of the supersolid. It turns out that if you take liquid helium and you try just to get this roton minimum to touch zero, that's to become soft in technical terms, things don't work out. This cannot work in liquid helium. But if we take Bose-Einstein condensates, so Bose-Einstein condensates, they are superfluid, and you can engineer them in different ways to actually imitate very much this roton spectrum. Yeah? So you have different techniques. You can have really this type of structure. And then what you could imagine is that maybe in some of these systems you could have this minimum touching zero and then the supersolid appearing. And actually, not all these systems work out, but some of them do. And what was shown a few years ago is that there are 3 different platforms where you can make these supersolids with Bose-Einstein condensates. So the first one that was demonstrated was a Bose-Einstein condensate that was placed in 2 high-finesse cavities. So it's a Bose-Einstein condensate that is coupled to light. And this system could crystallize. So here you see its crystallization. This is in momentum space, so it's a Fourier transform of what is happening in situ. And you see the crystalline structure. There were also experiments in spin-orbit coupled Bose-Einstein condensates. This is the system that we use, so I will discuss more in detail later. And there were then, a bit more recently, these dipolar supersolids. This is the system that Michele is working on, which actually have demonstrated really beautifully this supersolidity. And now when you have different platforms that in principle could show the same phenomenon, you would like to understand more in detail this crystal. So actually, the ones that have been studied more in detail are these cavity supersolids and the dipolar supersolids. And what was striking is that, yes, both systems spontaneously crystallized and they still remain superfluid, but the properties of this crystal, they were studied and they look pretty different in the two cases, because in this case, the properties of this crystal turn out to be like really rigid. This crystal is given by the mode in the optical cavities, so the spacing of the crystal is really fixed by the light wavelength, and yes, this crystal can move around or maybe it can change its amplitude, but it's still very stiff. Yeah? And then, on the contrary, these dipolar supersolids, they have much smaller crystals. You see here like 4 blobs, but they can do it up to 10 or something like that. But these crystals seem to be very alive, so it seems to be very flexible. So they could really, in the experiments, see how this crystal could move in time, have phonons and things like that. Yeah? And then you may wonder, well, what happens with these spin-orbit coupled Bose-Einstein condensates? So the spin-orbit coupled Bose-Einstein condensates, the supersolidity is also induced by light, like in these cavity supersolids. So there was first this misconception that, well, it should be the same, so this crystal should be fixed by the light wavelength. But then there were theory works saying, well, no, calculations seem to show that actually it's much closer to these dipolar supersolids. So as an experimentalist like me, when you have discussions and people are not agreeing and so on, you say, well, we should just do an experiment and try to figure out what happens. Yeah? Let's measure that, and then we will know everything. And that's what we did. So the system that we study is the spin-orbit coupled Bose-Einstein condensate. So let me tell you what it is. It's actually very simple. We take a Bose-Einstein condensate, superfluid, that has 2 internal states. This is 2 internal states of the atom that I will call spin up and spin down, or blue and green in all my presentation. And what we do is we join them via a 2-photon transition. So there is some excited state here, but we don't go on resonance to the excited state, but off resonance. And then with 2 photons with the right frequencies, we can couple the 2 states. So if you look in a rotating frame, the dispersion relation of the atoms looks like this. So in the blue state, it's a parabola. In the green state, it's a parabola. And these 2 parabolas, they are spaced by 2 times this Raman wave vector. This is actually because if you want to go from the blue state to the green state, you need to absorb 1 photon and re-emit 1 photon. So you get 2 momentum kicks, 1 per process. Yeah? And this is what you would get if there is essentially infinitesimally small coupling between the 2, which is given by this Rabi frequency here. This is the strength of the coupling. But if you increase the coupling, of course, this was a level crossing, and it becomes an avoided level crossing. So you have a gap that opens here that is given by omega. Yeah? And then you get like 2 bands, lowest one that I call minus and upper one that I call plus. And actually, if this gap is much bigger than all other energy scales in the system, then you can forget about the upper band. Yeah? So we will restrict ourselves to the lower one. And now, how does supersolidity come in here? Actually, it is very simple, because if you have a dispersion relation, really this is in momentum space, that has this shape, you could think that you have atoms, for example, that occupy the 2 wells. Yeah? So now, when atoms are in the blue well, actually, they are in a coherent superposition of the blue and the green, because they are coupled to each other. Yeah? So that means that they have a polarization. It's a spin composition that is mostly blue atoms, but it has a bit of admixture, coherent admixture of green atoms. And when they're in the right well, it's the other way around. Yeah? But this is in momentum space. But if you go in real space, everything is sitting in the same location. So that means that in the same location of space, you will have blue atoms that have 2 different momenta, and they can interfere. And then if they interfere, the interference pattern will give you some crystal. Yeah? But at the same time, this system is a superfluid, so it will be superfluid but crystalline at the same time, and that's how the supersolid comes up. Okay, so that sounds actually very easy, so why don't we just do it immediately and that's it? Well, there is a big but there, which is from the beginning I assume that you can occupy the 2 minima, but it's not necessarily the case. This depends on the interactions of these atoms dressed by the light. Yeah? So you will have atoms in the left well that will have interaction strength that is characterized by this coupling constant that I will call GLL, interactions in the right well characterized by GRR, and also interactions in between the two wells, because you have to think that this is momentum, but in real space everything is in the same location. Yeah? And now, if the interactions between the wells are smaller than the interactions in each well, then it will be very favorable for the atoms, and that's what they will do to occupy the two minima. Yeah? And that's where you will have this interference appearing, and then you will have the supersolid that is also often called the stripe phase because it has like stripes. Yeah? But if this interaction between the two wells becomes very repulsive, larger than the interactions in each of them, then this will cost a lot of energy, and the atoms will rather all prefer to go in one well or in the other one. And actually here, in principle, if the interactions GLL and GRR are identical, it will be spontaneous symmetry breaking, Z2 symmetry breaking. Sometimes they will go on one, sometimes they will go on the other, or if you have a big system, you will have domains. In some places, they will do one thing, in the others, the other thing. Of course, if they are not identical and one is smaller, the atoms will always go where the interaction is smaller. Yeah? So basically, you go from a system that is miscible, everyone is in the same location, to immiscible when these interactions between the two wells are different, so spatially separated regions. Yeah? And this is what you can compute, yeah? And you can compute that just by checking what are the effective interactions of these atoms in this coherent superposition, so you can do a simple analytic model for that and get these conditions. Then, of course, people did the experiment, and this is the experiment that was done in the US in the group of Ian Spillman in Maryland, and what they saw is actually something interesting, that you can start with a system that is initially mixable, and when you put this coupling, the atoms are just mixed. They are together, sitting together, but suddenly, when you increase above a certain threshold this coupling, then there is demixing, and then they go into this plane wave phase. So by changing the strength of this Raman coupling, of this two-photon process, you can go from one phase to the other one. And actually, you can understand why is that. This is really because when you have this dress state, this double parabola dispersion relation, if now I change the strength of the Raman coupling, then I will hybridize more and more the states, and the two minima, they will start to come more together. The spin composition of the states will change, and then interactions will also change. So you can actually do a bit more. You can do some theory and find the phase diagram of the system. So all the time I was discussing this axis, which is the strength of the coupling. This is what they did in the experiment. But you can have another parameter, which is the detuning, it's called. It's basically, do you have the two parabolas with the same energy to start with, or do you have one lower or the other lower? And of course, if one has a lower energy, then it's very easy that you put all atoms in one or all atoms in the other. And now, when you're an experimentalist and you see this phase diagram, you get very scared. And you get very scared because when you start to have axis that looks 10 to the minus 3 characteristic energy scale, you should get scared. That tells you it's a very, very small energy scale. Actually, this energy scale is so sensitive that if you have the elevator moving in your building, it creates some magnetic field and already changes the energy, relative energy of the parabolas. So that means that this stripe phase is super, super fragile. Yeah? And there is even some more worrisome thing. You could think, well, I tell people not to take the elevator, right? But there is something fundamental on this, which is that if you look on this axis, there is actually small Rabi coupling strength that already makes you go away from this supersolid phase. And what this is telling you is that actually there will be very little admixture of the other component in the other well. So the interference will be really having very little contrast, and that's going to tell you that this crystal will exist, but will be very hard to see for the atoms that were used in these experiments, which were rubidium atoms, because it's only a few percent. So you will have a superfluid with some tiny spatial modulation on top that will be very hard to see, and even if you see it, very hard to probe how this crystal is behaving and so on. And this is what actually motivated us to revisit this problem with a different atomic species, because different atomic species, they can have different interactions. And what we use in one of my group labs in Barcelona is potassium for the Bose-Einstein condensates. And as I said, potassium is very good because we can adjust the interactions. So actually it has two bosonic isotopes, so we can make Bose-Einstein condensates either of potassium 41 or potassium 39. And we can have different interaction properties in each of them, and also as a function of magnetic field. So for the supersolid experiments, we took this isotope, potassium-41, and what you see here is that when you change the magnetic field, and here we go around 50 Gauss, so about around 50 times the Earth's magnetic field, this parameter here, which is the so-called scattering length, this tells you about the strength of the interaction between the atoms, has this resonant behavior with magnetic field. So actually, depending where you put yourself exactly, then you can have very different interaction properties. And we select exactly this dashed line here. This is the parameters that we like. And we like these parameters because some years ago we did really some precise mapping of all these properties. And we know that exactly here we have the interaction properties that we like, because we have interactions between the two states and then between the two wells, essentially, that are much smaller than the interactions in each of the others. Yeah? And then when we compute the phase diagram of our system there, this is what we find, and we find that actually compared to before, we want 3 orders of magnitude in this axis and 1 order of magnitude here, so that's much more favorable to do an experiment. And I promised you that, okay, we need to get larger contrast of this crystal. Yeah? Well, if we go here and we check what the contrast will be for the crystal, then we see that we can get density modulations that go above 40%. So above 40%, that's something that would be much easier to probe and to characterize. So then to give you a schematic view of the experiment, so we have the atoms, the lasers that we use for generating this coupling. We set them at a very precise wavelength. It's very important that we use this wavelength because we want to make sure that these lasers cannot make any crystal, any optical lattice on the atoms, because that would be some explicit breaking of the translational symmetry. And this, at this precise value, we know this is not the case. And then we put these 2 beams at 90 degrees. And there are also constraints on the polarization such that this coupling process happens. This is all atomic physics details. And we know that the spacing of the crystal that we will do will be of this order of magnitude. This is the smallest spacing that we expect, which is 543 nanometers. Okay, so then the first thing if you make this system is you want to see how it behaves. So you remember that I told you about this dispersion relation and these 2 minima in momentum. So we want to probe that, first of all. And for that, we load the atoms in this dress state. Yeah? And then at t equals 0, what we do is that we switch off these coupling lasers. And that has, by effect, to switch off this spin-orbit coupling to project the atoms into the dashed lines, which are the original states. Yeah? So you will see, I mean, here the atoms are mostly in blue, but with a bit of green, and the other way around here. So when we switch off, we project into 4 spin momentum components. That's why all this is called spin-orbit coupling, because it's spin and momentum coupled. And then we can look at the momentum distribution of the atoms just by letting them expand, because when they expand, if they have high momentum, they will fly further than when they have small momentum, and this will just reflect then in the density distribution. And then we see the momentum distribution here, and you indeed see experimentally 4 peaks, yeah, which is what we expected. So this makes you happy, but then when you have an experiment like that, what is cool is that you can very easily repeat the experiment, changing the strength of this coupling. And with that, you can scan the phase diagram. And this is what we did here. So we start with essentially no coupling, and we increase it. And you see what we are seeing here is that initially the states in each of the wells are essentially blue and green. But as we increase the coupling, we have more and more admixture of the other component, and we have more and more weight of the side peaks. Yeah? And the other thing that we see here is that actually the position of the atoms in this minima that we can compute here to see the group momentum of one spin component or the other one also changes, because when we are increasing the coupling, the 2 states, the 2 wells, they start to come closer together. Yeah? So in momentum space, they get closer. So this is, we also measure experimentally. So when we saw this, we were pretty convinced that things were working pretty well as we expected, but we were still not at all satisfied, because we are measuring an ensemble property of the system, but who is telling us that actually this spin composition is right, but it's not that some parts of the cloud, they are mostly in the blue well and some in the green well, and then we are measuring the average and we think that they are together in space, but this is not the case. So really, if you want to show the supersolid, you should see the crystal. Yeah? And seeing this crystal is not so easy because this 540 nanometers is a small spacing. Okay, with a microscope we can see that, but actually with a microscope we can see single atoms. But here we will have many, many atoms. I mean, hundreds of atoms, thousands of atoms in each of the stripes, and this we don't know how to detect. So what people did in previous experiments was very smart, because they took the atoms, which have this density modulation, and they shine light, and they look at a particular angle where you expect to have Bragg diffraction from this matter crystal. Yeah? And then if you check in a camera, you can see that if you have no crystal, you have some diffuse light pattern that arrives to the camera. This is Rayleigh scattering. And if you have the density modulation, then you have some extra peak, black here, that is telling you there is a crystal. So this is very nice. This is telling you there is this crystal, but it's not telling you much about the spacing of the crystal, the contrast of the crystal, because you would need to really check the location of this spot on the camera, but you're really not very accurate on that. So you cannot say anything. That's why people did not address the properties of this crystal. So we thought that we would need to get a different trick to magnify this spatial distribution such that we can see it with our imaging system. And we came up with this scheme that was proposed in different contexts, which is the following. So we start with atoms in this double well dispersion, and at t equals 0, we just switch off this coupling, and we project into the bare spin component, so these 4 momentum peaks that I was telling you about before. But now, instead of letting them propagate in free space, we will just put a harmonic trap here, and let the atoms evolve in this harmonic trap for a quarter period until they come at rest. And then this is just very simple single particle physics. This is like first year physics course. Then after this quarter period, then what will happen is that we will have mapped the position, the position of the atoms will now reflect the momentum distribution. Yeah? You will see these 4 peaks that I was telling you before, because you exchange position and momentum. And then after this is done, then you just could let everything expand again, and you will map momentum into position again, so you will get a magnified image of your atoms. And then if we do that, first we did this sequence, of course, with the Bose-Einstein condensate without the spin orbit coupling and all that, just to see what happens, and we just saw, okay, it's small, and then we do this magnifier, and it's 6 times bigger. But then we did it where we expected to see the super solid, and this is what we saw. So this is really a direct image that we see after this sequence on our camera, and I think that there is no doubt that this has a very modulated spatial density profile. No? So this got us very excited, and we were expecting to see 1 cloud, but we figure out that if we tweak a bit this time, that it's not exactly quarter period, a little bit shorter, we would get 2 clouds that you are seeing here, and that actually these 2 clouds correspond to the 2 spin components, so we can actually see each of the spin components in this crystal experimentally. Yeah? So once you have that, of course, again, you want to scan parameters and see what happens. So we just scanned this strength of the coupling, and what we see is that if we put larger coupling strength, the contrast increases, and this is exactly what we expect from theory. And also, and I think this is more interesting, that if we increase the coupling, the spacing in this crystal is changing. So we are really seeing that the stripe spacing is increasing with this coupling strength. And this we understand very well is because this double minimum dispersion, when we increase omega, the minima, they become closer because the gap gets bigger. And the stripe spacing is the inverse of this momentum spacing here. So this is telling us that the period of this crystal is not fixed by the light wavelength. It also depends on the other parameters. And we even see more when we repeat the experiment. Depending a little bit how we prepare, we can have these points a bit up, a bit down. Like it seems we can excite this crystal, which is telling us that this stripe supersolid is not stiff. It really has some dynamics, so it's a spontaneously appearing crystal, and it's a crystal that has phonon modes, excitations in there. And this is what we are trying to do now, because when you have this supersolid transition, what people know in all the other platforms is that you expect to have a new broken symmetry. So you have the crystal and you have the superfluid. So you have 2 broken symmetries, so you should have 2 so-called zero-energy Goldstone modes. Yeah? So you can have in the superfluid phonons, sound waves, yeah, that cost infinitely small energy to just start to excite. And it's the same for the crystal. You can have this crystal, and this crystal could slide, and sliding the crystal essentially does not cost you anything. And this was seen in the dipolar supersolids, and here you see a numerical simulation of what we expect in our system, and we really expect to see the same, and we are really working on trying to get clean signatures of that in the lab. We can also attempt to do other things, which is really, if we start with a Bose-Einstein condensate with no supersolid, it will have some excitation modes, and then when we get into the supersolid, what you expect is that you have double the modes, and you have double the modes because initially you only had the modes of the superfluid, and then you can have of the superfluid and of the crystal, and we really expect very similar things in our setup, which we are also attempting to measure right now. Okay, so with this, I really finished this part of my talk, and let me tell you a little bit about another topic that we have been working on over the last couple of years, which is the simulation of gauge theories in the same type of setup. So we have our Bose-Einstein condensates, and we make them out of neutral atoms. So you would think that we cannot investigate the physics of charged particles in there because our atoms are neutral, but actually for many years, we know how to engineer synthetic vector potentials that couple to the atoms. And then, of course, if you have a synthetic vector potential, if you look at its time variation, you get electric fields. At its curl, you get magnetic fields. You can actually make gauge fields for these atoms. The point is that in most experiments that are done in our field, even though the particles in a BEC are quantum particles, these gauge fields are classical ones. And we wanted to go beyond that. So we wanted to turn our vector potential here, our gauge field, into a quantum mechanical operator that acts onto the BEC and also have back action from the BEC into the gauge field. So really to engineer quantum gauge fields for quantum particles. And actually, if you start to look at that, you can think of ways of making this a quantum entity. But if you want to do a theory of quantum gauge fields coupled to quantum particles, as soon as you talk to your theory friends, they tell you, well, better you take the right theory of fields. Yeah? So you should take gauge theories, basically. Yeah? And actually, even though it looks a bit intimidating for an experimentalist like me to just dig into this quantum field theory world, you can expect this to also be very rewarding because we know that, that gauge theories are really fundamental on our understanding of nature. And if you could do that with Bose-Einstein condensates, you could maybe think of emulating high energy physics. Gravity, gauge theories are also very important for describing effectively very strongly correlated materials. And this is, for example, an artist's view of spin ice. And even for quantum information science, I mean, Kitaev's story code, it's a Z2 lattice gauge theory. So if you know how to simulate gauge theories in your lab, so you know how to make your quantum gases speak this language of gauge theories, then you can simulate many more phenomena. And this is what motivated us during the lockdown time. So this is thanks to COVID, to actually open these quantum field theory books and try to understand what we need to do in the lab to engineer these gauge theories. So for understanding that, we started with QED because that's the simplest gauge theory that we know most about. And then, I mean, if you try to abstract what is the essence of a gauge theory, as we did, what is the essence of a solid, it does not look so complicated. Okay, you need to have matter and gauge degrees of freedom because you need to have like electrons and photons. Okay, so you have two fields. Maybe I can do a mixture for that. They need to be coupled in the right way, so you need to have minimal coupling, so you replace the momentum operator by P minus A. If we know how to do these classical gauge fields, we know how to do that, so it looks okay. And that's where it's not so nice. You also need to have local conservation laws that are fulfilled in every point of space and time, because you need to conserve, for QED, electrical charge. Yeah? And that is imposing you that the theory needs to be gauge invariant, and that tells you that every point of space and time, the gauge field and the matter field, they need to be linked because you need to fulfill the Gauss law. Yeah? And that turns out to be not so easy in these atomic physics experiments, but still, I mean, the motivation is so high that there have been a lot of progress over the last years, and it all started from theoretical proposals of people like Enrique, but now experiments are really getting there. And we have actually simulation of gauge theories in the three main experimental platforms in atomic physics with trapped ions, with Rydberg atom arrays, and with neutral atoms in optical lattices, as I explained before. But what all these experiments do is very simplified gauge theory. The simplest thing that you can think of that is non-trivial, which is QED, quantum electrodynamics, in 1 + 1 dimension, so 1 temporal dimension, 1 spatial dimension, and in a discretized version, because that's also simpler for experiments. So that's called the Schwinger model. So, okay, this is very nice, but if you think through that, okay, this is the simplest theory you can think of, and the first one that is not completely trivial, but it's kind of page 1 of the quantum field theory book. So you can then think, okay, can I just go beyond that and maybe go to volume 2 of the book, or maybe take other quantum field theories that are interesting, for example, for the description of many body systems. And this is where the frontier of research is now, how to go beyond this 1 dimension for QED. And this is what Enrique's team, for example, is working on. How can you just propose new schemes to do that? And in my group, we got interested into that, and actually we got interested in different classes of gauge theories, so-called topological ones. And the most famous example there, again, if you open the book, is what is called Chern-Simons theory. That, at first sight, looks like the same as QED, so maybe it's not so complicated. There are these matter and gauge fields minimally coupled. The local conservation law is different. In this case, it links the magnetic field to the matter density. They are proportional. And it's not Gauss law, it's called flux attachment. So when we came here, then I thought, well, we need to have intuition of what's going on. So what does it mean, this flux attachment? Can we have a physical example? And actually, you figure out that this Chern-Simons theory, this is a theory that is used to describe fractional quantum Hall states. So we try to understand the physics from there. So basically, fractional quantum Hall physics appear when you have quantum particles confined to a 2D plane and subjected to a very strong magnetic field. And in this system, the kinetic energy is very strongly reduced. That means that interaction effects, correlation effects are very important, and they give rise to cool physics. So you have a system with, for certain filling factors and so on, with excitations that when you exchange them, they are not bosons or fermions. They are behaving like something in between. They pick up an exchange phase that is any phase, and that's why they are called anyons. So it turns out that how Chern-Simons theory comes in here, that this is very complicated, strongly correlated state, but you can try to build some effective single particle model or weakly interacting model to get some intuition, and this builds on this idea of flux attachment, and this is discussed on the very first papers on the theory of fractional quantum Hall states. So the paper where Wilczek discusses anyons, he also discusses this flux attachment. The idea is that you replace the strongly interacting particles by some new weakly interacting particles, and you put all this effect of the strong correlations into the fact that these new orangish particles here, they grab part of the external magnetic field, and they get it attached to them. So then basically you get these composite particles, which are this orange particle and what is called a flux tube, like a small solenoid that generates some magnetic field. And now in this effective theory, fractional quantum Hall physics becomes simpler. For example, for the anyons, if you now exchange composites, you're exchanging solenoids, so you have an Aronoff-Bohm phase related to that, and that's how the anionic phase can come in. So that's nice, and then I mean, there is again this name flux attachment here. Well, where does it come from? Because if you check what's the magnetic field that is generated by all these solenoids, all these flux tubes, well, each particle has 1 or 2 or 3, depending on the fractional quantum Hall state you want to describe, but a number of solenoids attached to it. So the magnetic field that they all create needs to be proportional to the matter density. And this is exactly the relation that I wrote before. And actually, it turns out that at the end, you have these particles that are coupled to a gauge field, which is the one that gives this magnetic field. And this theory that describes how these particles couple to this gauge field is Chern-Simons theory. It's actually similar to electromagnetism, but it's like an electromagnetism where the photons are so heavy that they cannot propagate by themselves. They can only propagate when they are stuck to matter. And this is a theory that you could think if I remove all the matter, it's very trivial, because then the gauge field is not moving and so on. But it can have some non-trivial solutions if the vacuum has a topological structure and so on. So that's why these theories are called topological field theories. And this is the type of thing that we think we can maybe do. And why would you want to do that with Bose-Einstein condensates? Actually, people in condensed matter proposed this idea many years ago that if you could engineer things like Chern-Simons theory, it could be pretty cool because you could get anions without having very strongly correlated system. And of course, if you're interested in the anions because they are a proof of strong correlations, that's not good. But if you want to have anions, I don't know, for quantum computing, it might be a real advantage that they come in a system where you can write all equations and so on. Yeah? So there are actually cool proposals on how you could engineer this type of things in condensed matter, but they are hard to do, so nobody has achieved something. So we thought maybe we should try to do that with our quantum gases that we can control better. It turns out that Chern-Simons theory is still too hard, so we have theory students working on proposals for that. For experiments, what we look at is the reduction of Chern-Simons to one dimension. Yeah? And this is called the chiral BF theory. And it's actually the equivalent of the Schwinger model that we had before for QED. So the simplest model that is non-trivial, that has the essence of the physics, but for this new class of gauge theories. And it has some interesting physics. So this fractional quantum Hall states the physics in the edge is very particular. So you have so-called chiral edge mode. So you have the particles that can flow in one direction in one edge, in the other direction in the other edge. Yeah? And I will show you something that is actually the equivalent of that in this 1D theory. So maybe I will go a bit quicker here, but we have this 2D Chern-Simons theory, and this chiral BF theory that we will do is just a reduction to one dimension, and it's a theory actually that we did not invent. It was proposed in the 90s and studied in detail by people like Roman Jakif and his group. And what it has is actually this initial model has a gauge field coupled to a matter field coupled to a gauge field. And this gauge field has temporal component and two spatial components because it's a 2D system. And if you go to 1D, you get a model that has matter field, two components for the gauge field, it's 1 plus 1, so time and space. And then this vector potential in the direction that we removed, it goes into some new scalar field that is called B because it's bosonic. So when you read these papers, they tell you, and also the books, what model you need to do. Well, as an experimentalist, you get a bit scared because first of all, it's a Lagrangian, it's not a Hamiltonian, and it looks very complicated. So it has some gauge field terms. So actually this one reads BF. F is the electromagnetic field tensor, and that's what gives the name to the type of theory. It's a BF type theory because of this. And then it's a term that is chiral. This is actually a term that you need to put in this theory to make sure that you have these edge states that I told you before. And then you have here, this is easier, this I'm more comfortable with. This is just minimal coupling of matter and gauge field, P minus A. Yeah? And then you have interactions between the matter particles. This is also a simple thing. Yeah? Still, I mean, if you look at that, as an experimentalist, we know how to make Hamiltonians. This Lagrangian gets you uneasy. And also there are many fields, so it looks complicated. So you would like to find simplifications of that. But I told you before for electromagnetism that all these fields, they are not independent. They are linked by the Gauss law. So now for these, they will be linked by also some local conservation law. And for this theory, the conservation laws, they are linking B, N, and A. So we can actually use that to simplify and to do what is called encoding in matter. So we use all these local conservation laws to remove all these gauge and scalar fields and write everything in terms of matter. And this is a trick that we did not invent, actually was invented by the Innsbruck group in the context of quantum simulation. That's how they did the Schwinger model with the trapped ions. So of course, there is a price to pay. I mean, why you have this very nice gauge theory construction to describe electromagnetism? It's because then you have the gauge field that is doing the mediating interactions between the particles. If you remove the gauge field, the price to pay is that you will get some new emergent interaction term between the particles. For QED, it's just a Coulomb interaction. For our theory, is this new interaction term, which Jakif called chiral interactions, and actually it's just an unusual term for cold atom people, because normally we have interactions between the atoms which are density-density in the Hamiltonian density, so it's really like collisions between the atoms. But here we have current operator times density. So that's a bit funky, but actually it's quite easy to understand what it means. If I go in a semi-classical picture, if I have a wave packet, the current is nothing else than the density times the velocity. Yeah? So if I replace here, I find that this is the same as density-density interactions, but now I don't have a coupling constant that is a constant, but now I have interaction strength that depends on the velocity of the particles, on their momentum. And then that means that you will have a system where when atoms move fast or slow, they are having different interaction strength, and they will also be different when they move in one direction or in the other direction, and that's why Jacques called them chiral, these interactions. Okay, so then how do we do that in the lab? Actually, we take the same system as before, but instead of going to this double well dispersion relation, we put more couplings such that the dispersion becomes parabolic again. But you see that I have this color scale in this parabolic dispersion. This is because the spin composition is changing with momentum still. Yeah? And then there is another ingredient that I need to add, which are interactions between the particles as before. But in this case, what I want is to have these two interactions that are very, very different. Yeah? And why is that? It's because if I look at these dressed particles, yeah, then their interactions are going to depend on the polarization, which depends on momentum. So if I have large negative momentum, I'm mostly blue, yeah? So I will have interactions of the blue atoms. If I'm mostly large positive momentum, it's green, so I will have interactions of the green atoms, but in between, I will have something in between, and this is what we compute, that we expect in this system. And you see that if you put yourself in any point in this central region, yeah, then the interactions, they get proportional to the momentum, yeah? And we will exactly get this interaction strength that we want, and really this lambda term will be just given by the difference between this G up and G down down. That's why we want them as different as possible, to have as much tuning range as possible. Yeah? So this is how we need to do things, and this is a hand-wavy explanation, but we did all the quantum theory, so actually we can derive in this system the Hamiltonian of this chiral BF model at the quantum level, and everything works out. So then how do we do the experiment? So we take again our potassium experiment, but instead of potassium 41, now we have potassium 39. And we again chose some particular states there and a particular magnetic field, which just gives us the interaction strength that we want. So one interaction strength that is large and tunable, one that is very small, and interactions between the two states that is also very small. Yeah? And then the experiment is the same as before, just the lasers, instead of having them 90 degrees, now we put them like this. You will see in a moment, because we want to look at dynamics along this direction. And also, this is a 1D model, so we need to squeeze the atoms strongly, such that they are only doing dynamics in one line. Yeah? Okay, so then we do that. So what we do is we prepare atoms here, dressed by the lasers. And at t equals 0, I mean, initially they are confined by another laser that I did not draw, that comes through here. Yeah? But at t equals 0, we remove this laser, so the atoms will be able to move in this guide, in this line. And also we kick the atoms. We give them a kick either in one direction or the other direction. And we see that when we kick them to the left, the atoms are just moving without dispersion. So we have this wave packet of atoms that preserves its size. While when we kick them to the right, they start to expand. So you are clearly seeing that something is different between left and right direction. Actually, we can quantify that. We can see really these sizes, and you see one not changing and one changing. And we understand that from atomic physics point of view, because in this case, when we kick left, the interactions get effectively attractive, and this attraction is preventing the particles from spreading, while in the other direction, they are repulsive, so everything tends to spread. So it's a chiral system where left and right propagation direction are different, but it's not just that in this attractive case, the atoms are spreading less. They're actually not spreading at all, as you see here. And this is because they are forming what is called a soliton. So it's a self-bound matter wave packet. You have attraction that tends to put all the particles together, but then you also have quantum pressure. You have kinetic energy that does not allow that they compress forever. And then at some point, there is a balance between the two, and then what is called a bright soliton forms. Yeah? And then, okay, it seems when we kick left, we have this bright soliton, but I told you, I mean, in this 1D model, you expect to have chirality, and you expect to have that you can have some wave packet that can only propagate without dispersion in one direction and not in the other. So you expect this soliton to be chiral. Yeah? So to test that, we took this kicking to the left, yeah? And we just build a wall for the atoms. And this wall, again, it's very simple for us. We just put a laser beam that repels the atoms, and it's like a huge barrier, so huge that the atoms cannot tunnel through. And then when we smash our solitons here against the wall, we see that when they bounce off, they start to expand. So this is really a soliton that only exists in this direction and not in this one. And also, it looks like a particle that only exists in one direction and not in the other one. And this is really these chiral solitons that were predicted actually in the 90s for this chiral BF theory, but these were theory predictions, and now we give them reality in the lab so we can make them and play around with them. Okay, so with this, I really come to the conclusion of my talk. So I told you about what we can do with potassium Bose-Einstein condensates, these tunable quantum systems where we can study different many-body phases. So I told you about engineering topological gauge theories, this chiral BF model, and supersolids. That's what we are working on right now. And I also told you about basically using these cold atoms in optical lattices as quantum simulators for material science, really as analog quantum computers for material science. And I have to say that at this stage, our labs, they look very much like the first computers. It's really like a full room, a bit smaller than this one, full of lasers and optics and electronics and computers and all that. But we have this new addressability that we can really see in very much detail these quantum systems. And I think what is very interesting if one comes from condensed matter is that the things that we can measure in these systems are different from what people can measure in condensed matter. So it's really a very complementary view on the same type of physics problems. And with this, I don't want to finish without showing the group, because actually they are the ones doing the work. So we have 3 labs in my group, and also theory collaborations and several shared students with quantum optics team of Alessio Celli at the Autonomous University in Barcelona. And what I told you today is the work of the strontium lab for the microscope and the potassium lab for the exotic superfluids. And with that, I would really like to thank you for your attention. En euskera yo necesito traducción simultánea.
Congratulations for the very nice talk. I have a curiosity about the first part about the microscope. So you showed this picture where we see these atoms in a light. Now my question is, in general, it is possible to prepare the initial state a controlled way in order to fit evenly the optical lattice?
So yes, this is a very good question. I did not want to enter in details, but what I showed here, the first image, the big image, this is a thermal gas, so that's why there are holes, and there are also doublons that we see as holes and single atoms and so on. We can cool that more, so what we can right now do are superfluids, so we are in the superfluid regime in the lattice, so we make the BC, we get in the superfluid regime, and we can look at the momentum distribution using this matter wave lensing trick, and we see these superfluid peaks. And now we are working on getting Mott insulators. We are not yet there. It's like, well, we first write the paper on this because the students need to also defend their thesis. But we are, I think it's going to work in the coming weeks or months, to be able to prepare Mott insulators and then have unity filling n equals 2 or so. No. So in principle, there is no...
So they are flexible because there are many... aside from this field, so the current technology in general, in this experience allows to have...
It allows to use interactions between the atoms. If the atoms repel each other, you can actually sufficiently, and you can actually have a really like step-like distribution, and you can have 1 atom per side, and then 2 atoms per side, 3 atoms per side, and I mean 1 atom per side. For example, if you're interested in quantum registers or so, it's a very nice system because it's a very big system, really unity field, and then here, if we can see the atoms one by one, we can also address actually the atoms one by one with lasers through the objective, so you can take also using that also for different tasks.
I can watch the change. I saw normally experimentally it's difficult to observe the plane wave or phase catching. So I wonder whether it is interesting to apply the machine learning to recognize these things.
Okay. Okay, this is a good question. I don't think it's so hard to distinguish the plane wave from the stripe phase. What is hard, actually, it's a first order phase transition. So you have hysteresis and you have metastable states. So what is very hard is actually, I mean, if you start in one phase and you cross over, what we see is that we can keep the stripe phase by much longer than it should because the states remain metastable, and then it takes very long to decay to the plane wave and the other way around. So this, to me, it's more like an experimental problem, or can you introduce some dissipation or some coupling between the two that will help you in not getting stuck in metastable states and truly go to the ground state. And then, I mean, maybe that's an experimental perspective. It's harder from the experimental point of view than just the distinction of the phase. Machine learning, we are actually right now starting to play with for recognizing where each atom is here, because this is actually a cool reconstruction problem. We realize you need to take, like, the best thing are these astronomy tools. Yeah? They are very good at identifying objects that are nearby, and so they have developed lots of algorithms for that. But there are people now showing if you apply smartly machine learning, you can actually do better than the naive algorithms that we are first using. Yeah? Like, at least maybe reconstruct with the same fidelity, but much faster, or maybe even for smaller spacings.
Yo tengo una duda sobre el último experimento que tenéis. Tenéis como dos tipos de partículas, si se desplazan a la izquierda, si se desplazan a la derecha. ¿No? Una es como lo llamáis solitón, que no tiene dispersión, y el otro sí que se dispersa. Una de las ventajas de estos simuladores cuánticos es que puedes ver dinámica. Puedes estudiar la dinámica que tienes tu hamiltoniano y ver cómo podríamos construir estos wave packets y hacer que a una colisión de este
sí. ¿Qué pasaría ahí? Entonces hay distintas predicciones porque puedes también hacer dos solitones con velocidades distintas. No es tan fácil en el experimento y por eso no lo hemos hecho, porque hacemos la simulación y hay papers de esto. Y entonces cuando colisionan, depende de lo que pasa en la colisión. O sea, si por ejemplo rebotan, o sea, son dos solitones, rebotan, desaparece uno. Pero también se podrían unir entre sí y entonces tienen distinto número de partículas y se comportan, las interacciones efectivas son distintas y entonces se comportan también distinto. Entonces hay distintas cosas que puedes hacer, es más en el espíritu de física de solitones, que también se ha hecho de hacer colisiones entre ellos, es solo que este término nuevo añade una riqueza adicional, o sea, es más... Estos son cosas más parecidas a óptica no lineal, donde estudian este tipo de cosas, porque miran estas cosas para solitones ópticos, en fibras ópticas, pero no tienen este término de corriente, y entonces es interesante entender qué tipo de...
Podemos ver también como un scattering de partículas, ¿no? Una de esas que tiene esta dispersión y otra que se mantiene como más con solitón, o lo que
¿sí?
dices tú, dos solitones que se mantienen...
Y ves lo que sale después.
Claro,
¿No? Esto es interesante, interesante. Tengo que decir, lo que estuvimos mirando, dijimos, vale, pero hacer dos y tal es más esfuerzo, o sea, ahora mismo preparamos en una trampa, si no tendríamos que hacer dos trampas, no es mucho más esfuerzo, pero si hay ideas chulas, es un experimento que seguro podemos hacer.
That's related to the N squared potentially. You were stabilizing the system with the N squared.
Yes.
Which is where you have.
I write here. Huh?
So you have the chiral part from that one.
Yes.
But then you're stabilizing it with the N squared. If you're really liking these things, when you're going to the higher density, it's going to thoroughly next time.
Yes. So what we see, and this is a very good point, what we see is that we basically get this Hamiltonian, and now depending on the exact coupling detunings and so on, the strength of this GF can change. So if you start doing collisions and so on, you need to do them in some momentum range where this Hamiltonian is not changing. If you go beyond that, it will be a problem. For densities, if we go too high density, actually the problem that we will have goes beyond anyway all this frame, because if densities are too high, then we will have free body losses. So we have dissipative terms on top. No? But I think you can find a regime of parameters where you have densities low enough, even with two solitons, if you start with small enough solitons, that this is totally fine. I think it's trickier to find regimes where this mapping holds, and maybe I can even show here. It's very easy to understand what breaks down. So basically, no, it's later, sorry. When we look at our mapping, what we are doing is that we are assuming that for some momentum here, that this is linear around. Yeah? And you see that there is a range of momenta where it's linear, but then it curves, of course. Yeah? And all this thing works, and all this mapping of the theory and also the quantum model and all that works because we work with wave packets, which are Bose-Einstein condensates that don't have too big momentum spread. So actually, to derive this Hamiltonian, we do some series expansion in momentum, and it works because the momentum is weighted by the wave packet is weighted by the Raman momentum, which is much bigger, and all this in the perturbation theory and the Taylor series and so on. It's also weighted by omega. So basically, omega is very large, Kr is very large. So all these holds, but you see that if you go too far away in momentum, well, it bends. Yeah? So that these are the first correction terms, even before dissipative terms.
I have a question regarding the double weight. You said that there was another band, but the energy jump was so high that we could forget about it. Can you find a material where that jump is small enough so transitions can happen?
So this is an extremely nice question. So if we want to study conductor and band insulator physics and so on, we rather do on the lattice. On this lattice system, actually, if you look at the energy spectrum of the system, you have bands that look very much like materials, and you have conductors, and you can have then insulators because you fill the band, and they are conductors again, and so on. Here, actually, we are now restricting ourselves here, but we did some experiments where we occupy the higher band. And what is very cool is that then you can have collisions of atoms in the higher band that make them decay to the lower band. So we can have processes that go from one band to the other. And we did some experiments, actually not with a double well structure, but with a parabolic one. And you can create even correlated pairs, because if you have atoms that are colliding up and then they decay down with different momenta, I mean, you still need to conserve energy and momentum in this process, then these atoms, you have a halo of decaying atoms, and they are correlated, they are entangled to each other. No? So it's actually a cool thing also for other properties, and if you change the coupling properties, then you can change the rate of these decays, and you can go to configurations where there is no decay, and then suddenly you change it, and then there's a lot of decay, and so on. So we think it's a nice, very nice question, because it's a cool system to play with.
Pues si no hay más preguntas o comentarios, parecemos otra vez al